You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. The purpose of this episode is to build fluency in application, operations, and legal terminology. These terms represent the foundation of how secure cloud systems are built, maintained, and governed under law. Application terms guide developers and architects in designing software that withstands attacks. Operational terms describe the tools and processes that keep cloud environments visible, resilient, and adaptive. Legal terms translate technical decisions into compliance obligations that affect contracts, audits, and incident response. For CCSP preparation, this vocabulary is essential. Without precision in these domains, you risk misinterpreting exam questions or overlooking critical responsibilities in practice. This session ensures you can reason with clarity across the technical, operational, and regulatory layers that define secure cloud adoption. Application security is the discipline of building and running software with integrated protections. Instead of treating security as an afterthought bolted on later, application security embeds safeguards throughout the development and deployment cycle. It includes input validation, authentication, authorization, encryption, and error handling. Cloud amplifies the importance of application security because applications are exposed to global networks and shared infrastructures. In exam scenarios, application security terms remind you that resilience depends not only on strong platforms, but on secure code and design principles. In practice, application security ensures that business logic is defended against threats that evolve as quickly as development methods themselves. A secure software development lifecycle, or SSDLC, formalizes this approach. Security is integrated into every stage: requirements, design, implementation, testing, deployment, and maintenance. For example, during requirements, you define compliance needs. In design, you apply threat modeling. In implementation, you use secure coding practices. In testing, you apply SAST and DAST. And in maintenance, you patch vulnerabilities quickly. SSDLC is not one framework but a principle applied across methodologies such as Agile or DevOps. On the exam, SSDLC references highlight whether you recognize that security must be proactive and continuous, not reactive or episodic. Threat modeling is a structured method for identifying potential threats, attack paths, and mitigations. Techniques like stride-spanning spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege help teams anticipate how attackers might exploit weaknesses. The value lies not just in listing threats, but in prioritizing them and embedding countermeasures in design. For cloud applications, threat modeling accounts for distributed architectures, shared responsibility, and API exposure. For the exam, threat modeling concepts often signal the need for proactive reasoning, preventing weaknesses rather than only detecting or fixing them after deployment. Static application security testing, or SAST, examines source code or compiled code without executing it. It is like proofreading a manuscript to catch errors before publication. SAST identifies flaws such as injection vulnerabilities or insecure function calls early, when they are cheapest to fix. Dynamic application security testing, or DAST, takes the opposite approach. It probes a running application from the outside, simulating attacks against interfaces and behavior. It is like stress testing a bridge after construction. Together, SAST and DAST provide complementary perspectives, one static, one dynamic. On the exam, recognizing their differences ensures correct alignment between method and development stage. Interactive application security testing, or IAST, blends these approaches. It instruments an application during execution, capturing data from within the running process. This allows precise detection of vulnerabilities as the code operates in real time. Runtime application self-protection, or RASP, goes further by embedding defenses into the application itself, monitoring execution and blocking attacks as they occur. These terms reflect modern approaches to embedding visibility and protection directly into applications, rather than relying solely on perimeter defenses. For CCSP purposes, IAST and RASP highlight the evolution of application security into runtime resilience, adapting protection continuously. Software Composition Analysis, or SCA, addresses a common risk: third-party components embedded in modern codebases. Applications often rely on open-source libraries and frameworks, which can carry vulnerabilities. SCA tools automatically identify these components and check them against vulnerability databases, enabling developers to patch or replace risky dependencies. This is critical because supply chain weaknesses have become frequent attack vectors. On the exam, SCA references test whether you understand that secure applications depend not only on your code but also on the components you import. Application Programming Interface, or API. Security protects the interfaces that expose application functions and data. APIs are the backbone of modern cloud applications, enabling integration and automation, but they also create attack surfaces. API security covers authentication, authorization, rate limiting, input validation, and monitoring. Common risks include data leakage and denial of service attacks through poorly secured APIs. For CCSP candidates, API security terms often appear in scenarios where integration or multi-cloud environments introduce risks that perimeter controls cannot handle. OAuth 2.0 and OpenID Connect, or OIDC, are protocols that govern access and identity federation. OAuth 2.0 manages authorization, allowing one service to access resources on behalf of a user without exposing credentials. OIDC extends OAuth to provide authentication, verifying user identity across domains. Together, they enable single sign-on and delegated access common in cloud applications. On the exam, recognizing which protocol governs access versus identity is crucial. In practice, these protocols reduce password sprawl while centralizing trust and enforcing strong identity management. Secrets management reappears here as an application concern. Applications often require credentials, keys, or tokens to access resources. Poor practices, such as embedding secrets in code, create severe risks. Effective secrets management involves vaulting, controlled distribution, automated rotation, and auditing. It ensures that even if one secret leaks, exposure is minimized. For the CCSP, secrets management concepts remind you that identity and data protection are continuous responsibilities across all layers, including application code. Parameterization and input validation defend against injection attacks by constraining how inputs are handled. Parameterized queries separate code from data, preventing attackers from manipulating commands. Input validation ensures that only expected formats, such as digits in a date field, are accepted. These techniques illustrate that many vulnerabilities are preventable with disciplined coding practices. For the exam, they highlight concrete mitigations against injection, one of the most enduring risks in application security. Secure configuration management ensures that application environments use hardened settings and controlled changes. Default configurations, unnecessary services, or ad hoc modifications are common sources of weakness. By applying baselines, enforcing least privilege, and tracking changes, configuration management reduces exposure. Automation tools can enforce consistent settings across environments. Exam references to Secure Configuration Management Test, whether you recognize that resilience depends not only on design, but on disciplined, repeatable implementation. Continuous integration and continuous delivery, or CI/CD, pipelines automate the process of building, testing, and deploying software. These pipelines increase speed and consistency, but also create risks if not secured, such as compromised build servers injecting malicious code. Protecting CI/CD involves validating code, securing credentials, and monitoring pipeline activity. For CCSP learners, CI/CD references emphasize that automation must be paired with governance, as the speed of deployment magnifies both benefits and risks. Blue-green and canary deployments are release strategies that manage risk. In a blue-green deployment, two environments run in parallel, one active blue, one idle green. Updates are deployed to green, and traffic is switched over once validated. Canary deployments release changes gradually to a subset of users, allowing issues to be detected before full rollout. Both strategies provide rollback options, reducing the impact of failures. On the exam, these terms highlight controlled release as part of secure operations, ensuring resilience in the face of inevitable software changes. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Security Information and Event Management, or SIEM, is a central platform for aggregating, analyzing, and correlating security telemetry from across an environment. Logs from applications, infrastructure, and cloud services are fed into the SIEM, where they can be queried, visualized, and used to generate alerts. SIEMs support both detection of incidents and compliance reporting, since they provide a unified record of activity. For example, unusual login patterns or spikes in failed API calls can be surfaced as alerts. In CCSP contexts, SIEM references highlight the role of centralized visibility and analysis, bridging technical events with governance and response requirements. Security Orchestration, Automation, and Response, or SOAR, builds on SIEM by automating workflows across security tools. Instead of analysts manually triaging alerts, SOAR can enrich them with context, trigger predefined playbooks, and even execute responses such as isolating a host. This reduces response time and frees human resources for higher value analysis. SOAR embodies the principle of scaling operations to match the speed of cloud threats. Exam questions may emphasize how SOAR complements SIEM, with SIEM focusing on detection and SOAR focusing on coordinated action. Cloud Security Posture Management, or CSPM, continuously evaluates configurations against standards and policies. These tools scan cloud resources for misconfigurations, such as publicly exposed storage buckets or overly permissive roles, and recommend or enforce remediation. CSPM reflects the shift toward automation as the only way to manage complex, dynamic cloud environments. For exam preparation, CSPM references reinforce the shared responsibility model. Providers secure infrastructure, but consumers must configure it correctly. A Cloud Workload Protection Platform, or CWPP, provides security for workloads across different environments, virtual machines, containers, and serverless functions. CWPP spans the lifecycle, protecting workloads in build pipelines, deployment, and runtime. Features include vulnerability scanning, runtime defense, and compliance checks. The key is consistency. Workloads are protected wherever they run, across on-premises, cloud, or hybrid. Exam questions often use CWPP as shorthand for workload-level defenses, complementing CSPM's focus on configuration. Cloud Infrastructure Entitlement Management, or CIEM, is an emerging category that addresses identity and permission sprawl in cloud environments. CIEM tools analyze who has access to what, detect excessive privileges, and recommend least privilege adjustments. With thousands of roles and policies in large deployments, manual oversight is impossible. CIEM ensures that identities, human and machine, are governed at scale. For the CCSP, CIEM reflects the growing emphasis on identity as the true perimeter in cloud security. Vulnerability management is the continuous cycle of discovering, assessing, prioritizing, and remediating weaknesses. It relies on scanning, patching, and reporting, but also on governance to ensure issues are addressed in timeframes that match risk. The key insight is continuity. Vulnerability management is never finished. For CCSP learners, it underscores that resilience depends on staying ahead of evolving threats, not on one-time fixes. Service-level agreements, or SLAs, define contractual commitments for availability, performance, and support. They are measured by service level objectives, or SLOs, and tracked through service level indicators, or SLIs. For example, an SLA may commit to 99.9% uptime, with SLOs defining the threshold and SLIs measuring actual availability. These terms appear on the exam to test whether you can align contractual obligations with operational realities. Business continuity and disaster recovery, often abbreviated as BCDR, ensures organizations can continue operations during disruptions. Continuity emphasizes maintaining essential services, while disaster recovery emphasizes restoring systems after failure. Together, they protect not just data but business operations, aligning technical measures with organizational survival. In exam contexts, BCDR scenarios highlight governance and planning as much as technical resilience. Digital forensics is the structured acquisition and analysis of data to support investigations. It emphasizes accuracy, repeatability, and integrity, ensuring findings stand up in legal or compliance contexts. Chain of custody supports this by documenting every handoff of evidence, preventing questions about tampering. For CCSP candidates, these terms highlight the intersection of security and law, reminding you that investigations are not only technical but also procedural. A Data Protection Impact Assessment, or DPIA, sometimes called a Privacy Impact Assessment, or PIA, evaluates how a project or system handles personal data, identifying risks and mitigation strategies. These assessments are required by many privacy regulations, particularly when new technologies or processes could affect individuals' rights. They represent governance in action, embedding privacy by design. Privacy laws like the General Data Protection Regulation, or GDPR, and the California Consumer Privacy Act, or CCPA, reshape how organizations manage data. GDPR establishes strict rules for processing personal data within the European Union and for data about EU citizens. CCPA establishes similar rights for California residents, including access, deletion, and opt-out rights. For the exam, these laws remind you that compliance is global, and often extraterritorial data protections apply based on the subject, not only the system's location. Data processing agreements, or DPAs, and standard contractual clauses, or SCCs, are contractual instruments that allow lawful cross-border data processing. They allocate responsibilities between processors and controllers, and SCCs provide standardized terms that satisfy regulatory requirements. These agreements illustrate how contracts serve as governance tools in addition to technology. Breach notification obligations require organizations to notify authorities and sometimes affected individuals within defined timeframes after certain incidents. For example, GDPR requires notification within 72 hours of becoming aware of a breach. These obligations shape incident response planning, since speed and accuracy are essential. For CCSP learners, these terms emphasize that security failures have not just technical but legal and reputational consequences. Records retention schedules document how long different records must be kept and how they should be disposed of. These schedules balance compliance with efficiency. Some data must be kept for years, while other data must be securely destroyed after its use ends. Improper retention creates risks of regulatory violation or unnecessary exposure. On the exam, Record's retention scenarios highlight the governance layer of data management, ensuring that lifecycle and compliance principles are consistently applied. In summary, mastery of application, operations, and legal terminology ensures that secure cloud practice is not fragmented. Application terms reinforce building security into code and pipelines. Operational terms ensure visibility, resilience, and governance at scale. Legal terms tie decisions to compliance, contracts, and accountability. For CCSP candidates, fluency across all three dimensions demonstrates not only technical expertise but professional maturity. This vocabulary supports precise implementation, effective operations, and defensible compliance, equipping you for both the exam and leadership in cloud security practice. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.